Welcome back, listener. Today we're going on a deep dive, and today's topic is Dyson spheres. We're going to delve a little bit deeper than the typical portrayals you see in science fiction and really get into the science of it all.
That's right. We'll be looking at things like the stability issues surrounding them, the different forms they could take, even how we might go about trying to detect one, all based on the latest scientific research.
Sounds fascinating. So to start us off, why don't we go back to where this whole idea even came from?
Well, the concept of the Dyson sphere was really formalized by physicist Freeman Dyson back in 1960 in a paper titled Search for Artificial Stellar Sources of Infrared Radiation.
Catchy title.
Yeah, well, scientists. But Dyson himself actually took inspiration from a 1937 science fiction novel, Star Maker, by Olaf Stapledon.
Oh, I've heard of that one.
Yeah, well, in the book, Stapledon describes a civilization that uses swarms of structures to harness the energy of their star. And this is really important because from the very beginning, Dyson was thinking about a swarm of objects, not the one giant solid shell that we so often see in popular culture.
Right, that makes sense. And it's that distinction between the swarm and the solid shell that leads us right into the question of stability. Why are solid Dyson spheres considered so unstable?
Well, there are three main types of instability that would affect a solid shell:
Okay.
gravitational instability, radiation pressure instability, and mechanical instability.
Each one is a pretty big hurdle, it sounds like, for any budding galactic engineers out there.
Oh, yeah, you could say that again.
So let's break them down one by one. Why don't we start with gravitational instability?
Okay, so imagine you have this perfectly spherical solid shell completely enclosing a star. Now, because of how gravity works, the shell wouldn't actually experience any net gravitational force from the star inside it.
Really?
Yep, it's counterintuitive but true, which means it wouldn't be held in place by the star's gravity at all. So even the smallest little nudge from, say, a passing comet or something could cause the sphere to start drifting, and eventually you'd have a very big, very unfortunate collision.
Ouch. Not a good outcome. So it's almost like the sphere is balanced on a knife's edge with nothing to really keep it centered.
Precisely.
Okay, so that's gravity. What about the radiation pressure instability? How does the star's own energy play into all of this?
Right. Well, stars are constantly emitting photons, and these photons, they exert outward pressure on anything they hit. So in the case of our solid Dyson sphere, this radiation pressure wouldn't be applied evenly across the entire surface. You'd have things like stellar flares that would cause uneven radiation, which would push on the sphere unevenly. And that would just make the instability from the lack of gravitational centering even worse.
So not only is the sphere not being held in place properly, but it's also constantly being bombarded by uneven forces from the star it's
Yeah.
supposed to be surrounding.
Mhm.
And you mentioned a third challenge too, right? Mechanical instability.
Right. Even we could somehow ignore the gravity and radiation pressure problems, the sheer size of a solid Dyson sphere would create immense stresses on the structure itself, just from its own mass.
Yeah, that makes sense.
I mean, we're talking about forces far beyond what any known material could withstand. That would inevitably lead to buckling and fracturing and eventually total collapse of the sphere.
Okay, so it seems like those beautiful solid shell depictions we see in science fiction are just not scientifically feasible. Which brings us back to Dyson's original swarm of objects concept. How does that address the stability concerns we've been talking about?
Well, a swarm is, by its nature, a much more distributed system. Instead of relying on one massive structure, you'd have tons of independent objects, each with its own stable orbit around the star. And that neatly avoids the issue of gravitational instability because each object is individually balanced in its orbit.
Got it. So instead of having one single point of failure, you have a multitude of objects, each doing their part to capture energy.
Exactly.
And that also helps mitigate some of the risks from those external forces.
Yes, it would be much more resilient overall.
Are there any other potential shapes for a Dyson sphere besides a swarm?
Well, one idea that gets tossed around is the concept of concentric spinning rings.
Spinning ring.
Yeah. Picture a bunch of rings all orbiting the star at different distances, all connected and spinning fast enough to create outward centrifugal force.
Interesting.
That force could be balanced against the inward pull of gravity, essentially creating a structure that's held together by its own spin.
Kind of like a gigantic interconnected gyroscope.
Exactly, like a gyroscope, using rotational forces to keep itself stable.
But even with these more dynamic designs, are there still challenges when it comes to maintaining stability over the really long term?
Absolutely. Even a swarm or a system of spinning rings would still have to deal with all the other gravitational forces from objects in the star system,
Right.
like planets or passing stars. Maintaining that delicate balance over astronomical timescales would require some pretty sophisticated station-keeping systems.
Constantly adjusting and fine-tuning things to make sure nothing goes off kilter.
Precisely. It's an incredible engineering challenge. Really pushes the limits of what we can even imagine.
That brings us to another important aspect of Dyson spheres, the energy dynamics. We've talked about structure, but how would a Dyson sphere in any of its forms interact with the star's energy output?
Yeah, that's a great question. It's a complex interplay, and to understand it, we need to think about the path that photons take once they're emitted from the star.
Look,
We can model these interactions by looking at things like the fraction of starlight absorbed by the components of the Dyson sphere and the fraction of thermal photons that are re-emitted by those components. It's a fascinating dance of energy absorption, re-emission, and potentially even reflection back towards the star.
this is where things start to get really interesting. To help us visualize this, maybe we could use a simplified model, like a spherical shell, to see how these different factors affect what we might observe.
Absolutely. Let's do that. Okay, so we've got this hypothetical spherical shell surrounding our star, and this shell, it's got certain properties, reflectivity, absorptivity, transmittance, things like that. And those properties dictate how the photons from the star interact with the shell itself. Some photons will be reflected right back towards the star, some get absorbed by the material of the shell, and then some might even pass right through the shell, depending on how thick it is, what it's made of, that sort of thing.
Right, so the journey of each photon is determined by the shell material's properties.
Right.
Okay, so then how does all of that tie into what astronomers might actually observe when they're looking at a star system that could potentially have a Dyson sphere around it?
Well, these interactions, they directly affect what we can observe about the star system. For example, if you had a shell that was highly reflective, the star would appear much dimmer than you would expect for a star of its type, because a lot of the light is being bounced back inwards.
Ah, that makes sense.
But on the other hand, if the shell is very absorptive, well, then it's going to be capturing a lot of that star's energy, which would heat the shell up,
Right.
and that would cause it to emit thermal radiation, mostly in the infrared part of the spectrum.
Okay, so astronomers could search for Dyson spheres, not just by looking for the structure itself, but also by analyzing the light coming from the star system itself, looking for these telltale signs.
Exactly, that's right.
So are there any specific observational strategies that astronomers are using in this search?
Oh, yeah, definitely. The search for Dyson spheres has been going on for decades, actually.
Right.
Some of the early attempts used data from infrared telescopes, like the IRA satellite, the infrared astronomical satellite.
Right.
But more recently, searches have been using data from telescopes like WISE, the Wide Field Infrared Survey Explorer, and the Spitzer Space Telescope. Both of these are much more sensitive and have better resolution, especially in those infrared wavelengths where you'd expect a Dyson sphere to be radiating.
So the focus is on finding stars that are giving off way more infrared radiation than they should be, which could be a sign of some kind of warm, energy-absorbing structure around them.
You got it.
But I imagine it must be tricky to distinguish between something like a natural infrared source and a potential Dyson sphere signal.
Right. Oh, it's incredibly difficult. The universe is full of things that emit infrared radiation. You've got dust clouds, star-forming regions, even entire galaxies. So to try and pick out a Dyson sphere signal from all that noise, you have to be really careful. You need to analyze the data very meticulously, and often that involves combining data from multiple telescopes that operate at different wavelengths.
Right, so you're trying to build up a complete picture of what's going on.
Exactly, and the Gaia mission has been a huge help with this.
Gaia.
Yeah, it's a space observatory that's been mapping the positions and movements of stars in our galaxy with incredible precision.
Okay.
And that data, it's been crucial for separating those galactic infrared sources from extragalactic ones, which helps to narrow down the search.
So it really is a massive undertaking.
It is, but it's also incredibly exciting.
Now, are there any other strategies being used besides looking for infrared excess?
Well, another interesting approach is to search for what we call optically underluminous stars.
Optically underluminous.
Yeah, these are stars that appear much dimmer in visible light than they should based on their other properties. It's like something's blocking or absorbing a significant chunk of their light.
Which could be a Dyson sphere.
It could be. Although it's important to note that natural phenomena like thick dust clouds could also cause dimming.
Right, so it's not a foolproof method, but it's another piece of the puzzle.
Exactly. Another clue in the search.
So we've got a multi-pronged approach here using all sorts of different observational techniques and data sets to try and find these hypothetical megastructures. It's really quite amazing.
It is. It's a true testament to human ingenuity and our drive to explore the unknown.
Now let's talk about another crucial aspect of Dyson spheres. Efficiency. Assuming a civilization could actually overcome all the immense engineering challenges of building one, what factors determine how efficiently a Dyson sphere can capture and utilize energy from its star?
Right. Well, the efficiency of a Dyson sphere, basically how much of the star's energy it can actually use. It really comes down to three things: its size, its temperature, and the specific tasks that it's designed to perform.
Okay, so break that down for me. How do those three things affect efficiency?
Sure. So to understand this better, we can actually think about the work a Dyson sphere might do in two main categories. We've got low entropy emission or mass creation and dissipative work.
Those sound a bit abstract. Could you elaborate on what those actually mean?
Sure. So low entropy emission or mass creation is all about using energy in the most efficient way possible. In theory, a Dyson sphere could be designed to convert a big chunk of the star's energy into low entropy radiation. It's like concentrating and redirecting that energy for specific purposes. This could involve emitting beams of highly focused radiation or even potentially creating matter, things like antimatter, which requires a huge E amount of energy.
Antimatter creation, that's straight out of science fiction.
'Cause it is pretty wild, right? But it highlights the incredible energy scales that we're talking about with Dyson spheres. Now, dissipative work is different. It involves processes that, by their nature, release energy as waste heat.
Huh.
Think of it like a computer processor. You know how it generates heat when it's running? That's dissipative work. That waste heat increases the entropy of the system, which means it reduces the overall efficiency.
So a Dyson sphere doing things like computation would need to have a way to deal with all that extra heat.
Exactly. And often that means having a much larger surface area to radiate that heat away into space.
So it's a trade-off.
Yeah.
The more dissipative work a Dyson sphere is doing, the more waste heat it generates, and the bigger and more complex it needs to be to handle that.
Exactly. It's a balancing act.
So this raises an intriguing question. Could there be incredibly efficient Dyson spheres out there that operate at very low temperatures? Ones that minimize waste heat and would be really hard to detect?
Now, that is a fascinating thought. If a civilization really wanted to maximize their efficiency and stay hidden, they might try to create a Dyson sphere that emits very little radiation.
Like a stealth Dyson sphere.
Exactly. But to do that, they would have to optimize the design to perform its tests with as little energy loss as possible and then dissipate whatever unavoidable waste heat there is over a massive surface area.
Yep.
That would lead to a very low overall temperature for the entire structure.
So we're talking about a megastructure that's incredibly cold and potentially invisible to our current detection methods.
Potentially, yes. It would be a truly awe-inspiring feat of engineering, pushing the boundaries of material science and thermodynamics.
But there must be huge challenges involved in designing and building something like that. What kind of obstacles would they have to overcome?
Well, one of the biggest challenges would be managing the momentum that's imparted by all the starlight that's being absorbed. You see, photons, they carry momentum. And when they hit the components of the Dyson sphere, that momentum has to be dealt with somehow. Otherwise, the whole structure could get pushed away from the star by the radiation pressure. They might need some sort of intricate system of light sails or other mechanisms to counteract those forces.
It sounds like a delicate balancing act, trying to keep a structure of that size stable while also harnessing all that energy.
It really is. And then there's the question of practicality. I mean, even if you could build a cold, stealthy Dyson sphere, what would its purpose be? If the goal is just to be undetectable, well, then maybe it's doable. But if the Dyson sphere needs to actually do something, like power a civilization or run massive computations, well, those tasks are going to generate heat, which makes it much harder to stay cold and hidden.
So there's this inherent tension between wanting to minimize waste heat for stealth
Yeah.
and needing to actually generate energy or perform tasks that inevitably produce heat.
Exactly. It's a fundamental trade-off. And it really makes you think about the priorities of any civilization that would consider building a Dyson sphere. What are their goals? What are they willing to sacrifice?
It's a fascinating thought experiment. It really highlights the interplay between physics engineering and the choices that a civilization would have to make when undertaking such a monumental project.
Absolutely. And it speaks to the sheer scale of ambition that would be required to even attempt something like this.
Okay, so let's imagine for a moment that a civilization does have the capability to build a Dyson sphere. Where would they even begin? What would
Right.
be the first steps in such a massive undertaking?
Well, the first thing they'd need to do is take stock of what they've got. They'd have to figure out what resources are available in the star system. They'd need to find a star that's going to stick around for a long time, a star with a stable energy output. And they'd also need to analyze all the planets and asteroids, figure out what they're made of and where they're located, because that's going to be their raw material for building the Dyson sphere.
So it's like a cosmic inventory, mapping out the entire solar system and cataloging all the potential building blocks.
Exactly. It's a massive undertaking.
Once they've done that, what comes next?
Well, then they'd need to develop some pretty advanced technologies for extracting and processing all those resources. Think self-replicating mining robots that can break down asteroids and planets. Maybe even orbital foundries and manufacturing facilities to refine the raw materials and create the components for the Dyson sphere.
It's hard to even fathom the scale of an operation like that. We're talking about dismantling entire planets and asteroids.
Yeah.
Boggles the mind.
It does, doesn't it?
And what about energy? How would they power all of this?
In the beginning, they might have to rely on more conventional energy sources like nuclear fusion or fission, maybe even harnessing energy from their home planet or other easily accessible resources. But as the project progresses, they'd probably start using the star's energy itself to power everything. It's like bootstrapping their way to a more powerful and sustainable energy source.
Using the very energy source they're trying to capture to fuel the construction process. That's pretty clever.
It is. It speaks to the incredible ingenuity and resourcefulness that would be required for a project of this magnitude.
So they've got their resources. They've figured out how to power everything. How do they actually go about putting the Dyson sphere together?
Well, the assembly process would be incredibly complex. It would likely involve swarms of autonomous robots working together to carefully position and connect all the prefabricated components. They might start with a ring or a partial shell and gradually expand it over time. It would be a slow and meticulous process.
A delicate dance of engineering on a solar system scale. So let's shift gears a bit and talk about motivation. Why would a civilization even want to invest so much time, energy, and resources into building a Dyson sphere in the first place?
The most obvious reason is the energy. A Dyson sphere could capture a huge portion, if not all, of a star's energy output. It would give them access to power on a scale that we can't even imagine.
It's the ultimate power source, tapping into the heart of a star to fuel a civilization's growth and ambitions.
Exactly. And beyond just raw power, a Dyson sphere could also serve as a massive habitat. You could create an interconnected network of structures orbiting the star, providing a controlled environment where people could live and thrive.
It's like building a world that spans an entire solar system.
Exactly. It's a vision of a civilization that has truly transcended its planetary origins.
What about from a scientific perspective? Could a Dyson sphere be used for research or exploration?
Absolutely. Imagine a Dyson sphere as a giant observatory, able to peer deep into the cosmos, or as a platform for conducting experiments on a scale that would be impossible on a planet. The scientific possibilities are endless.
It's a tool for unlocking the secrets of the universe, for pushing the boundaries of knowledge and understanding.
Exactly. It's a testament to the potential of science and technology to help us explore and understand the world around us.
But as with any technology this powerful, there are also ethical considerations. What are some of the dilemmas that a civilization might face when considering building a Dyson sphere?
Well, one major concern is the impact on other planets in the system. If the construction process isn't managed very carefully, it could disrupt planetary orbits or even destroy planets completely. A civilization that can build a Dyson sphere would have a huge responsibility to consider the effects of their actions on the entire solar system.
It's a reminder that technological progress should never come at the expense of other life or the delicate balance of nature.
I agree. And there's also the question of what happens if other civilizations are out there. The existence of a Dyson sphere would be a pretty clear sign of a highly advanced civilization, and that could attract attention, maybe even unwanted attention.
It's a classic science fiction scenario. But it raises some very real questions about the potential risks and rewards of contacting other intelligent life.
It does. It's a topic that deserves a lot of thought and careful consideration.
Let's go back to the science for a minute.
Yep.
You mentioned earlier that astronomers are looking for transiting megastructures. Can you explain what that means?
Sure. So transiting megastructure searches are based on the same principle that we use to detect exoplanets. It's called the transit method. When a planet passes in front of its star, from our perspective, it blocks a tiny bit of the star's light. And we can detect that as a dip in the star's brightness using telescopes.
Wow.
So the idea is that a Dyson sphere, or even just a part of it, could also cause a detectable dip in a star's brightness if it passes in front of the star.
Makes sense. But wouldn't it be hard to tell the difference between a planet and a megastructure?
It would be challenging. Yes, planets usually cause very small periodic dips in brightness, whereas a Dyson sphere might cause larger, more irregular dips depending on its shape.
So astronomers would be looking for those unusual patterns in the data.
Exactly.
Are there any other ways that astronomers might be able to detect Dyson spheres?
Well, there are a few other ideas. One is to look at the polarization of starlight.
Polarization.
Yeah, it's basically the direction that light waves are oscillating. Most natural light sources emit unpolarized light, meaning the waves are going in all sorts of random directions. But artificial structures, like the ones that might make up a Dyson sphere, could potentially emit polarized light.
So if astronomers see a star that's emitting a lot of polarized light, that could be a clue.
It could be. It's like a fingerprint that could betray the presence of something artificial.
Fascinating. And I think I remember reading somewhere that we might be able to detect radio emissions from a Dyson sphere. Is that right?
That's another possibility. If a civilization is using radio waves for communication or energy transmission or other things, we might be able to pick up those signals.
So it's like listening for whispers of technology across the vastness of space.
It is. It's a long shot, but
Yeah.
it's certainly worth looking.
All of these different approaches to finding Dyson spheres.
Mm.
It really shows how multidisciplinary this search is. It's bringing together astronomy, physics engineering, even computer science.
It really is. It's a testament to the collaborative spirit of science and our insatiable curiosity to understand the universe and our place within it.
It's incredible to think that as our technology continues to advance, we might develop even more sophisticated ways of finding these hypothetical megastructures. Maybe one day we'll have definitive proof that we're not alone in our desire to harness the energy of the stars.
I certainly hope so. It would be a profound discovery, one that would change our understanding of our place in the cosmos forever.
Well, thank you so much for joining us on this deep dive into the world of Dyson spheres. We've covered a lot of ground today, from the science and engineering to the ethical considerations and the search for evidence. It's a topic that captures the imagination and reminds us of the vastness of the universe and the infinite possibilities that lie within it.
It has been a pleasure, and I hope that our conversation has inspired our listeners to keep exploring, keep questioning, and keep looking up at the stars with a sense of wonder and possibility.
Until next time, keep those questions coming, and we'll see you on our next deep dive.